few slides, and then in the second half, I'll share my screen and we can do some hands-on with the system with the turtle here. And since there's so few of you, then maybe we can also give everybody a turn, just changing the plan we made, adding goals, and sending the robot around doing some tasks. The first half of the slides, I'm going to cover the basics of ROS. I know you had a tutorial on this yesterday, so I'll go quite fast through it. But can I just get a show of hands on who uses ROS all the time and is comfortable with it? Okay, it's less than that. Let's start. Okay, so ROS is an open source library, a large set of libraries in robotics. I gather that your tutorial yesterday focused mostly on packages, on downloading packages, installing and compiling. For me, the main components of ROS is a running system of nodes and messages. ROS is a network of nodes which can be running distributed, sending messages to one another. So here's some example packages that you might know. ROS, I'm using Indigo on this robot, but it doesn't matter if you have a different version. So navigation is a package for localization and moving over around. Turtlebot package contains a whole load of useful utilities for the Turtlebot, automatic docking on the docking station, a 3D model of the robot, stuff like that. MongoDB store is just a ROS wrapper for the MongoDB, the Mongo database. So it's a relational database, and it's wrapped into a single ROS node, and you can store messages into it, which is really useful. And then the bottom there is ROSPlan, which in the second set of slides we'll cover in a great amount of detail. Let's concentrate on nodes for now. So when the system is running, a whole load of nodes will be running. Some on one computer, some maybe on this one. In these diagrams here, these circles are nodes, and these squares are message topics. So this is an example of a node move base. You send in a transformation to the move base, and the message topic hasn't appeared because it's never been sent when I made this go up. But you also send in a goal location, and then the node will output command velocity to move the robot. So that handles all the pathfinding internally, and it just has a set of inputs and a set of outputs. Another example here is AMCL, which is also this one's actually doing the localization in mistake. The AMCL takes in this scan topic. On this Turtlebot, looks at the connect data and takes a slice of that to use a fake laser scan, and it's a depth image. And it matches this against a map that it knows to decide where the robot is in the map. And then it outputs the transformation of the robot, the odometer. And if you remember the previous slide, this is one of the inputs for move base. Move base, I mean, if you're going to do some pathfinding, you need to know where you are. So you can see how these nodes will begin to connect up into a larger framework. Okay, this is the set of nodes that comprises ROSPlan. So ROSPlan is 3 main nodes. You see at the end there's, I know the name of a bit long, so a bit of boxes, but at the end is the scene database, the knowledge base, and the planning system. The inputs to these nodes are going to be the problem data that make up the PDDL model that we care about, and then the output will be the dispatch of the plan. We'll go into detail on that in a little bit. So when everything's running on this Turtlebot, this is the set of nodes that we're running. This isn't all of the topics. This is just the nodes and a couple of topics. But you can see that there's a lot of stuff involved. It's very rare that one person running a robot is responsible for every single bit of it. So yeah, here we have the sensor data coming out of the Connect. It's being converted into this fake laser scan, which is then used to get the odometry data by mapping the laser scan against the map to tell where you are. And then this outputs the transform, which is the position of the robot, so the move base can use velocity commands to pilot the robot to its goal positions. Point cloud data is output from the Connect, so you can see 3D images, maybe pass them to human skeletons or make a 3D map. Or you can pass it into some other node which recognizes objects based on color and shape. And of course, you also are updating the PDDL model stored in ROSPlan, and ROSPlan is sending out PDDL actions, like go to this position, which is then picked up by move base, and the robot moves again. Okay, so let's go back to this. The input are the goals, the PDDL goals, and sensor data. Sensor data has got to be passed and made into a plan model, and the output from the ROSPlan are the actions that should be dispatched for the robot to achieve these goals. And inside, it's doing the plan. Can I get another show of hands of who's a planning person? Right. There's most of you, because it's ICAPS. It's not everybody. This is ROSPlan again, but with a few more nodes shown. So let's start with the main components. The PDDL model is stored in a single node. This node, all its job is to store a problem instance and to answer queries and to be updated continuously. So you've always got a problem instance that's the current version of the world. And that's stored in the ROSPlan model base. And you see it communicates with the planning system, usually through queries or just pushing knowledge into it. The scene database is actually just a MongoDB server, which is renamed the scene database, and it stores some real knowledge. So if you're doing classical planning, you might have set waypoints around the map, and you want to say, go to waypoint 3, all along those lines. But move base needs coordinates in order to actually pathfind and find the route. So you need to store those coordinates somewhere, and they don't belong in the PDDL model. So you have the scene database to store all of the real information about the world. All it does is store messages in a key value database. The key is the object name, PDDL object instance name, and then the value will be whatever message you like. And you can store numerous messages under a single object. Finally, the planning system does most of the work. It asks for the problem instance from the knowledge base, passes this to the planner. The planner will produce a plan, and then it will dispatch that plan to other libraries like move base or whatever you have. And let's talk about that a bit. So, the simplest loop, the simplest algorithm the planning system could be is, while you still haven't achieved your goals, request the problem, plan, and then dispatch it. And once the dispatch is finished, either you've completed it or if you haven't, it's because the plan failed or because the model was wrong. Or, I don't know, anyone got any ideas what other problems there could be with this? I was here for a lecture a few days ago, and Nick Hawes asked the same question: what could go wrong when dispatching a long-term plan? Anything. Everything.
No question.
Are you still considering you just have one goal? Maybe you have a repeated goal or multiple goals or things strange. So that's not
Repeated goals is really one from repeated goal, that's right. You get those a lot. And my answer that day was, what happens if the model is wrong? The PDDL model doesn't capture something important and the plan fails. If you request a problem, try again, and it'll just fail again because your model's wrong. And worse, what happens when the model's wrong, the plan doesn't fail, and keeps going? That's when terrible things happen. That's when the robot thinks, I can go downstairs. And then, what's that? Which happened last week to this one. For the first time. So that's a bit simple. So we'll return to that later. But let's look first at how you dispatch the plan, because that's more interesting to me at the moment. So, I mean, we know what the output's got to be, because it's got to be in terms of ROS messages that's understandable to these nodes that are actually performing the execution of the actions. So move base knows how to do pathfinding and movement. So we have to make sure that the message we send to the loop bases in terms that you understand. It seems fairly simple, but can anyone see an immediate problem with this plan here? Or at least a difficulty with dispatch here?
What do those numbers mean? They mean
This
exactly the time when
this is the time the action is scheduled to be dispatched.
and it's perfectly admissible that go to waypoint is scheduled at time 1, let's say.
Yeah.
So these are lower bounds. So there's no. I'm asking him.
So for anyone who's run a planner, you'll probably get output like this, where it says at time 1.345 seconds, dispatch inspect location. What happens if the go-to waypoint takes longer than 1.35 seconds? I mean, you can dispatch it anyway, but is the plan still valid? Do you know? Or is the whole, is the thing that you're meant to inspect gone by now? What happens if go-to waypoint finishes before 1.345 seconds? Do you just wait and then dispatch it on schedule? Or can you just go straight ahead and go ahead and just dispatch it straight away? Because, I mean, you could solve the first problem by making really conservative estimates of the times of actions, really conservative. But again, Nicholas pointed out that sometimes that still doesn't work. When someone gets in the way of the robot and doesn't let it pass. And then if you have really conservative actions, estimates, and you decide you have to wait for the end, you have to wait for such a long time. It goes to a waypoint, you wait 3 minutes and then it goes to the next waypoint. You want to do that. It's an interesting topic right now. So inside ROSPlan, we store the plan not as a list of actions with dispatch times, but as an SQL program. So SQL is a synchronous programming language. The reason we use that is because it's got a very simple translation into state charts. State charts are just like a flow chart of the plan. So each node in this flow chart is an action from the plan. And the nodes are linked causally, so you know that this node has to be completed before this node can be started. The nodes also have upper and lower bounds on their dispatch times. So now you know exactly what the lower and upper bounds of these actions are in comparison to other actions. And finally, each of the nodes has start, overall, and end conditions, which are just the PDO conditions. Before you dispatch the action, certain things must be true. And during the dispatch, for all of the movement, the robot has to be on 2 wheels. If that ever changes, then the action has failed. Either because someone's picked it up or because it's doing a roly-poly, as it says. The dispatch, so then an SQL interpreter inside ROSPlan just interprets this graph and dispatches the actions one at a time. These external conditions, the PDL conditions, are checked using queries to the knowledge base. So when it's time to dispatch an action, we're inside the time bounds, all the causal links are satisfied. It makes a query to the knowledge base saying, are these facts true and wrong? If they're all true, then the action can be dispatched to the knowledge base. If they're not, then if it's an invariant, then the action has failed. If the deadline is passed and the time bounds are no longer valid, then the action has failed, the plan has failed. So this goes some way to making it possible to dispatch a plan robustly without making any guesses as to whether it's okay to dispatch an action late. Is there any questions about this? More commentary about it?
If you don't mind, just branching out a little bit. So there's the formalism provided by Smash and ROS.
Yes.
What was you're not using it, right? So this replaces it.
I think they're essentially the same thing.
Right. In fact, my question was, is there a reason to prefer this to Smash or?
So right now, no, I mean, Smash is probably more easy to use. As long as you have a pass the output of the plan into the Smash plan,
Sure.
and then you're good to go. The reason we chose SQL is because we've got our eye on some future work involving recursion and loops. We want our plans to also have loops and recursion within them. I'm not sure if Smash supports that yet. The advantage of the SQL program is that it's a Turing-complete programming language, so whatever we decide to do in the future, we can do. this is an example of how the conditions are checked using queries to the knowledge base. So we have three actions that are supposed to be executed concurrently, action A, B, and C. And A has this invariant. So, for example, consider there are two submarines, two automated underwater vehicles, AUVs, and they're supposed to go to two different locations. A is the action for moving one, and B is the action for the other moving. But the durations of these actions can be very variable, because you don't know what the currents are. And because of the currents and the path that the first submarine decided to take, B reaches its locations and blocks the passage of the first one. And this invariant, the path is clear, becomes violated at the end of the action B. It's something you didn't expect or plan. The plan and model didn't anticipate this. So at this point, this action is checking its invariant against the knowledge base. As soon as this pattern becomes false, it says, hold on, I can't complete this action, and it will report failure to the planning system. And the planning system is smart enough to do something about it. And the default is just to cancel the plan and say, okay, abandon everything. Send cancellation requests to every executing action, which will hopefully make it fail gracefully, but it depends on the libraries you're using. Okay, so going back to that top level loop, this is the case where we've called this batch plan and it's returned false. Because one of the actions failed and the plan, or the plan has failed, so the whole leash is false. So in this loop, we would say, oh, okay, B is in the way, we can't get through, let's just replan. And maybe the new plan is to move A out of the way, move B through, like that, but maybe that's not possible, and you're then stuck in a loop forever. So this is one of the most annoying things when you say, okay, robot, do something, and then it just repeatedly tells you, I can't do it. There's a number of reasons this can happen. Your model isn't good enough, there's good errors in it, and it just, you know that the robot is capable of solving the problem. It doesn't. It can easily work itself into a dead end that it didn't anticipate because of these model errors. The third one's a real challenge. It's a whole other topic where how do you make a plan in which you plan to discover new objects? And how can you plan to manipulate those objects before you know where they are or what they are? And the simplest thing to do is to just plan to discover them. Once they've been discovered, then say, well, that's good, now let's plan to manipulate them. But ideally, you want to interleave these things. If you've got a whole pile of stuff, you'd want to take an object off, look at it, take another object off, go, these can be combined over here. But like I said, then go back and look at the next thing, rather than just inspect everything and then. So this is a bit simple as a top-level control. And isn't the idea of ROSPlan that planning should be a top-level control? Really, we've just got planning now as a part of this very simple script. So, fortunately, this top-level script isn't fixed inside ROSPlan. It can easily be changed. One of the ways the ROSPlan planning system can be activated with a ROS message. You send a ROS message to the ROSPlan planning system saying, here are some goals, here's the plan I want you to use as input. And then as output, the ROSPlan planning system says, okay, I achieved those goals, or no, I didn't achieve those goals, we found some sort of dead end. This is just like any other node, like the loop-based node. You pass the goal you wanted to achieve, it goes away and it returns succeed or failure. So this means the planning system itself could be PDR action. You can have a plan that includes stopping, planning, and executing that plan. This is just one possibility for the top level. So in particular, the idea of ROSPlan is that these different components can be removed and replaced with your own stuff. So if you are doing some research into the way you can pass sensor data into a PDR model, maybe using some of the frequency analysis that Nick was talking about, then you can store that PPO model in the knowledge base, but you don't have to code your own plan dispatch if that's what you're not interested in. You don't have to automate the process of passing that problem to a planner and receiving the plan. Alternatively, if you want to use Smash to dispatch the plan, just get rid of the ROSPlan dispatch and put Smash on it. The knowledge base, the C database is there to automatically pass the sensor data to create the problem instance, to pass the plan, and then it will go to your Smash dispatch. And it should speed up the whole process of just getting the system together and running it. I'm near the end of my slides now. The last 2 slides are just to explain what we're going to do. I'm going to try and share this screen and run some things on the mobile. So first of all, I don't know, yesterday, did the tutorial cover how to run ROS on multiple machines at once? Okay. So with robots, it's a very small thing to learn. It's really important unless you want to open the laptop that sits on the robot and then chase it about. It's just not very convenient. So I find it something that you only have to learn once, and then it's very useful if everybody knows how to do it. Second, how do you launch it? So you must have seen this before. You use ROS run or ROS launch, but I don't know, we can. I'll do that while sharing the screen to show you just how it works with the system, and in particular how it works with ROSPlan. We can then explore some of the nodes that are running, topics and messages, so we can see what kind of sensor data is the Connect passing out, and what other nodes are running in this system. And then finally, all of that is nice, but you won't be able to understand point cloud data if it's just streaming in a console. You need some sort of graphical representation of it. And that's the reason why I need 2 machines, because I want to be able to look at what the robot can see on this one. And I'll show you how to do that. And then we'll play with ROSPlan for a bit. So ROSPlan has an RQT plugin. This is a window with drop-downs and buttons and such that lets you add goals, facts, dispatch single PPL actions, or dispatch plans. Okay? Let's do that. I said I'm about halfway through, so we're going to do another half an hour or so. And then anyone who wants to stay and play that can do so as long as they like. Is that visible? Is that font too small?
Quite small.
This small?
You can use Control Plus.
Control Plus?
Yes.
I think you're right click on profile preferences.
There we go.
So that's right.
Right? Can everyone see it? Or can anyone not see it? Right, let's go back. Alright, let's start with starting. Setting up ROS to run on multiple computers. So okay, this is very, very simple thing. On this, I'm on the wrong one, I'm on my laptop. On this laptop, we have to check the IP, they're running on the same network. And then on the other laptop, I add that IP with the robot's name. And you have to do this on both ones. So this laptop in the etc/host file, calls that one's name and IP, and on this one it calls this one's name and IP. And if you're ever using a robot and you're able to send messages to that one fine, but for some reason the visualization isn't coming back and no messages are being received on this one, it's because you've forgotten to do one or the other of those two things. Or one of the keys has changed. The second is, so open a new tab. If I do a ROS topic list, you see that there's no ROS core running yet on this laptop. But we do have the core running on this. Yes, you are. So in order to have this laptop use this one as master, you simply export one environment variable. And you can use the name from the host file. For some reason I get in trouble when I just try to use the IPs exclusively, and I have to add those names. And you see everything going on. So in ROS we have one master running through the ROS system, whose job it is just to connect publishers to subscribers. So when a new node is started, it says, I publish this kind of message, and he will connect that node to all the nodes that subscribe to that kind of message. I like to have a master running on the robot, so everything's as fast as possible here. And everyone else's PC will have to export this environment variable with the robot's master. Now everything can be seen from this console. And that's it. I have like an outline of this part. And I'll make it available afterwards in case anyone forgets that and really wants to know. As I said, it's a very simple thing, but it'll save time setting up if you just get in the habit of remembering it. Okay. So now, let's see about launching everything. So to launch a node, you know it's ROS run in it's running on the laptop. So my name is Michael. Michael laptop is my laptop sitting there at the top bottom. And his name is W, and this is his. So, for example, we could run move based directly on this laptop. On this one, we could run one of those visualization programs by removing the package name. So the package name is ours, and then the name of the executable is also ours. You can't see the splash screen has come up on this one. Drag it over. This has popped up. There we go. We have a lot of warnings and errors because the only node I'm running on this right now is web-based, and this is listening to all these different topics that I'm publishing anything. We'll come back to all this a little bit. So let's have a look at the launch file. So did you, any of you use launch files in the previous tutorial? Did you just use ROS running with nodes?
We use launch files, but we have mostly copy and pasted things from tutorial.
I mean mostly just copy and paste from previous launch files. Add comments.
So it was more of seeing, looking at RBiz, looking at Nick's robot through RBiz and seeing what it does, more so than learning mechanics across.
Okay. Let's go right here. So this is what's doing. Is that even visible in this cover?
Not really.
Not at all. Maybe less instead, maybe white at least. Okay, this is the standard ROSPlan launch file. It's meant to be just an example. You expect it to modify and add your own components. But we'll go through it. I'll explain what each part is and let you know how to start ROSPlan, as well as maybe a bit more about launch files. So launch files are useful for launching whole collections of nodes at once. If you remember the graph I showed at the start of all the nodes that are running on the Turtlebot when all the systems up, there's no way you just want to run every single one of those randomly, and they take a lot of different parameters. And that's when these launch files come in. So the first parameter is quite simply, this is just a domain file. So each time you start a ROSPlan instance, the knowledge base starts up and needs to read in a domain file. We use this to build the problem instance. So currently it expects the domain file to stay the same. In this case, we can look at that domain later. The knowledge base doesn't take any parameters apart from the domain path, which is global parameter. And you can start that without any difficulty. So it's the ROSPlan knowledge base package and the knowledge base node. The scene database is just, as I said, it's the MongoDB store package, and it's a MongoDB, which is a ROS wrapper around the database. In this case, there are two nodes that comprise MongoDB. You can find more information on that on the website. I think that is Nick Hall's and his colleague who's got
Dave.
It's not that one, it's Chris or something. But they are the maintainers of MongoDB, so if you see them around and you want more questions about how to use the database within the system, go to ask. I've had no problems with it except for one port issue which I solved on my laptop. That's all there. And then final one of the three is the planning system. This is the one that takes the most parameters. But the three parameters included in this are the data path. This is where the plan files are going to be stored and the problem files are going to be stored. By default, anytime a problem instance is generated, it's stored with a unique name so that you can look back at it. And the same with plans. The problem path is where it's going to save the problem instance, specifically the code. And the planner command is the string bash command, essentially, of how you want to run the planner. In this case, we are running popf and the planner popf with the timeout and the optimization flag on. So actually, it's an early version of optic we have on this that continually tries to optimize the plan until this timeout kills the process, and the final plan will be saved here. But this parameter can be replaced by anything. As I mentioned before, you can delete that and include your own plan. Sometimes it calls your own plan. Or for one project, we simply have this line output a plan file, just cat the plan, and have a pre-scripted plan that we'll follow. Okay. Back. This is the launch file I'm just about to run, a bit less. Okay, it's significantly larger. And it includes other launch files, which are part of the Turtlebot's packages. So these are just including other launch files that are loaded from other ROS packages. The Turtlebot printout will start up all the hardware. The AMCL will start the odometry, the scan, matching, connect, and all of that. And finally, the Kabuki auto docking just starts a few nodes that allows you to auto dock the robot onto this charging platform. This is just wood. These ROSPlan loads are exactly as I showed you before. And you see now the planning command is slightly different. It just explicitly says where you want to put the problem and domain file names. And finally, there's just some other nodes here. So, for example, we have a waypoints file that's going to be loaded and saved in the knowledge base, so it'll be part of the planning model. We have this move base interface that's going to go to waypoint actions and send those to move base. And we have other interfaces for auto docking and talker. I like to run something that means the robot will shout anytime it's about to execute a PDB action. Or if it falls down the stairs, the laptop flies off. You very sadly say, "Where am I?" Like that. Lost his organization. Okay. So I think the best thing to do is to run it all and start playing with it. So I'll launch the same launch file I just showed you. Let's have a look. When you create the launch file, begin with it first. Prints out all of the parameters that were loaded. Most of these are from those included launch files inside the total one. They are to do with the hardware. Then it lists all of the nodes that have just been started. Here are all the ROSPlan nodes. The knowledge base, the planning system, scene database. All the processes start, then we get output. All of the output from ROSPlan is a little KCL tag for ease of debugging. But that's it, that's everything running now, and this thing is ready to plan. So let's take a look at those graphical interfaces. So you've seen ours before. So, dock this guy. Moving the dock into the wall so that when he tries to auto dock and it's just standing free, so you have to push it around. If you back it up to a wall, then you'll properly auto it. Right. Okay, is the map visible? So this is the map of the stage area. The reason all these chairs are out is because that's the height that the Kinect does a laser scan. And if the chairs weren't here, it would think, I can just go over there and they'll take a tumble off the step. Well, you might not. There are cliff sensors on this which should stop the robot as soon as it peeks out over the edge. As I found out last week, you cannot rely on those.
Would it remember that there was an edge there?
So it would detect that there's an edge.
And the back up?
The wheels would lock and it would flip forward.
Oh, that's
It might be that I've just set the speed too high, but I don't want to lower it. That's for cowards.
Okay. Because I've seen some sort of default behaviors that say, oh, I'm going to plan to go over there. Oh no, there's a cliff here. Let's back up out of the cliff. And then go, oh, I'm going to go over there. And so on, goldfish.
Yeah, so I'm relying on the move base, I've said many times, to do all the pathfinding for me. And the current version is pretty good. Occasionally it will get stuck, and the default behavior is just to rotate on the spot for a little while. And it does this to try and clear the cost maps, which I'll talk about in a second. And that sometimes works.
I mean, that also helps if some of the obstacles have moved, so you have to rebuild some of the map.
Yeah. Okay, so this pink line, there's the robot. This pink line is that laser scan. It's looking at the chairs right now, which means, you can tell it's absolutely not localized. In fact, it's standing somewhere here. facing this way. This is the podium. These are the metal plates here. I walk in front, you should see my legs.
The map itself, was that built earlier? Did you send it on and did it have a look around the stage? Or?
Yeah, so I had Eric do that. Eric was one of my PhD students and had to do it last night. So he sat controlling the keyboard, piloting it around. He generally have it piloted separately.
Alright.
And you run another node, which isn't running right now, that continuously builds the map from the laser scan data.
Okay, is it sort of reasonably clever about exploring? Does it follow edges or things like that?
It went a lot better than I expected it to, because I've seen it. It's a difficult problem, so it's the SLAM problem, simultaneous localization and mapping. So you get the laser scan, and you say, okay, there's a wall there, I'll put that in the map. You get another laser scan, and say, okay, I'll put that in the map, and I know where I am, because I'm checking against the map, so I'll put it there in the map. So you know where the laser scan is, because you're checking against the map, and you're checking against the map, and building the laser scan. So any errors will, if you try to map a very long corridor, you might find it starts to go like that.
Yeah.
It gets a bit strange, but there were no such errors in this. Everybody just drove around in a big circle and it built this really quickly. So, and it's a very simple environment. It's essentially just a rectangle with a couple of obstacles in it.
And sorry, this kind of services are already, there are nodes into ROS that manage this thing. Okay.
So, there's a single launch file you can use called Gmapping.
Never used ROS, so I'm just.
Yeah. But yeah, you can find it if you go to all the navigation tutorials, then you'll see one on mapping. That is a couple of different SLAM mappings. We used Gmapping last night. It was good, and it does that for you. It's nice. So this is the static map. This is the map that you expect not to change, and it won't change. If I started moving furniture around, that would appear on this map. This is the map that's used for navigation. It's got a threshold value, so it's a cost map. You can see every obstacle in this now has a kind of aura that's letting you know exactly how close the robot can get to the edges. Though it's hard to tell on the screen, but it's gradient in colour, so it goes from light blue to like a hard yellow colour, I think. And the lighter the colour, the more easily the robot can get there. So as it gets close to a wall, it should slow down and try to be a bit more careful. It won't, but that's fine. When we send the navigation goal, it'll be with this map that it finds a global path to the goal. To follow the global path, it creates little paths in a local cost map. You can see this is bounded by this square shape. And this map is just to map, you can see I'm in it. It's just to map obstacles that are temporary. So if the person stands here, it will make a little local path around me that still tries to follow this global path. You see that I've left some obstacles behind. If the robot was to turn, I don't know if it will turn, then those obstacles will get cleared up as it sees that actually there's free space there. It's not bad.
Am I keep interrupting you with questions?
Yeah, we've got 2 hours and I'm almost finished. So.
Okay. You said earlier, and it's kind of obvious, that right now it's in a different position than it thinks it is on that map.
Yeah.
Is there a relatively quick way to tell it, hey, press a button, please look around you a little bit better and decide that you're actually here? Or
So the easy way is to use this button in Arbis. The hand will give you 2D pose estimates.
That's nice.
Where you click where you think it is on the map and you drag the direction you think it's facing. I'm not sure.
So it still requires you to give it to
So it's behind me on the podium here, and it's pointing.
okay.
But if you move it around a bit, it should localize, no?
Yeah, so
I thought, yeah, something like similar to particle filters.
So these are the AMCL particles. When I gave a post estimate, it made this distribution of arrows going,
Right.
oh, we think it's all here.
Mm.
I better unplug the laptop. It's just going to move. If I give it a path to follow before localizing it, it would have gone some misrange, and I don't want to risk that. But if I give it a path now, just to move forward and turn a little bit. Really slowly. There you go. You can see that it moves on the map a little bit. Alright, that's the recovery behavior I was talking about. That path I gave was too difficult for the base, and it's trying to recover. Fortunately, that's localized it really well.
Can I propose something? We can't, yeah, can we sit on those chairs?
Yeah.
I don't think there are lots of places in the room where we can actually see the robot.
Yes, where's it going? It's nice to be able to give it a navigation goal. I'll send over there. So you can also send navigation goals to the other. This is updating fairly slowly. And that's because it's running on this laptop. All of the topics being published. So each of these is essentially it's a topic being published, the messages coming out of the topic, and that laptop is subscribed to just to visualize it.
Oh, so this is a bit
Yeah. So this is a bit laggy because it's on the network. That's why I like to put the master and all of the nodes on the robot, so there's no lag, especially in the Connect data. Have a look at some of the Connect data. So if you want to add a new thing, you can add it by type, or you can actually just browse all of the topics that have been published. But let's get the image on the camera to Connect. So you just pick the topic. These are all the topics that are currently broadcasting an image. They're all from Connect. Regular or color image. Oops. There's W. It's a bit slow. It's okay. That's all. Since we're looking at school 30. Let's take a look at the depth image. The closer something is, the darker it becomes. This is connected to the 3D camera. Is there a nicer way to look at that? What's the same?
We'll have 7 figures.
It's not perfect.
It seems like it was just double image.
Yeah,
So it doesn't. So for the depth, it obviously uses the 2 cameras.
So it shows you
so
the overlap.
I believe there's emission perception of those emission.
So we use the 2 cameras. That's right.
One thing that as you get closer, you vanish at a certain distance from the camera. This was pretty good. But you know, there's the robotic receptionist right now in the downstairs in Hall, who saw that coming in. It shows your skeletal tracking, and you can see this. It's like this, but it's a thermal image. And as you move your hand closer to the camera, at about 30 centimeters, it goes black and vanishes. It's because it's doing it bounce. It has a minimum range. And that's something you have to remember when you want pathfinder just to connect at the time. This depth image is the one that's being used to create that purple laser scan. Let's get that laser scan. Oh, sorry. So it's taking a slice of this depth image and and then just putting values into the 2D space here. You can also use this image to create a point cloud and just project that into the space. You've seen those before.
Yeah, unfortunately, I have to go.
So there's you guys in 3D.
We look better.
We can color it. So if we will this work? It would slow, it might work. Yeah. RGB. There you are. The one thing I'm doing at the moment, just sort of research thing, I'm just using other people's code, is to do that slant mapping in my house using 3D colored fonts. So I have a nice 3D map in the house. Myself sitting at the desk. Really autonomously, so I don't want to manage all of that. So that I'll use a plan.
No, that's not. It's easier when you tiny
Welcome to Uncanny Valley.
That's his face.
I'll look at something from Minecraft.
I'm just turning it off because broadcasting all that data over the network will slow everything else down. So just turn it off and so we'll turn it on again. Yeah, so let's give it a back pose. Now, let's open up RQT. So ARP is really useful for seeing what the robot sees. RQT is just another graphical tool. It's a little different. It's more useful if you want to change and reconfigure the robot while it's on. It's on the other screen. So I'll try to get it up. So you can get a lot of plugins where, for example, there's this node graph plugin. It's quite useful. This is the one I use to create those graphs in the slideshow. So if I type, you see now it was planned. Oh, you know what? Did I export the master? Oh no.
I'll just cut the feed and record it again.
Yeah. So most of what we're seeing here is robot specific. Where are the planner ones?
So the panel ones are inside the ROSPlan. So let's simplify. Oh, there it is.
Okay.
So here's ROSPlan. Well, that's the ROSPlan interface. Maybe it's in the top. It's probably too big. There it is. So on the left you have circular modular nodes. So here's the knowledge base. Sending stuff up, way up. There's loads of things coming into it. Oh, that's right. Here's the planning system. You see it. This is one of the topics that is dispatching, which is actually this topic. And here's another topic that is receiving, which is feedback. It's also sending feedback because it is itself an action. When you ask it to plan, it will send feedback to the layers above it, which could be another instance of ROSPlan.
If you want to do, because I'm just thinking that number of nodes and topics that I'm seeing here are for something fairly basic version on this. So I'm just thinking for a way more complex robot, is the complexity going to be hidden away in your code in one node, or is that just going to be 5 times bigger?
It depends how you design it.
What's the best way to design it?
Of course, the best way to design it, that's a big question. It really depends. So on the one, if you go too far one way, you just got, you can put all of this into one node, one program that runs everything, that does all the scan matching, collects connect data, and does the planning and dispatches the plan.
And it's impossible to debug.
Yeah, and then you give that code to a PhD student and say, right, learn how to use this, and then make it do something else. And it won't happen. And if you go too far the other way, you'll have so many nodes, and each node is essentially just receiving a message and then passing it on without really doing any work.
Yeah.
And this is, this is the same sort of question again, object-oriented design, programming stuff. Okay, what should one class encompass? And it's up to the designer. I don't think this isn't too big. If you imagine this as these nodes, instead of being most nodes as classes, essentially they are. This isn't a huge industrial application, this is a small app. And considering the amount of work that this is doing, I guess it's a reasonable number of nodes. A lot of these are topics as well, right? I can hide the topics, I think. Hide the names of these topics, I think. And then I believe this is just nodes left. No, this doesn't work. It doesn't matter.
But what's at the top? Are they are those find functions at the top of that, or are they even?
These are part of the plugin that I'm using, the node graph that's letting you view different things. So I'm going to load some different plugins. As soon as I source my workspace, I assume you all know that you must source the workspace, so at least put a source line in your bash RC.
Yes, the line that you're typing on is all the Okay, fine.
Okay, so these are the ROSPlan plugins you are using, and they're all just part of ROSPlan, which you download and install it. You use those. Let's pop that up here. The simplest one is this. This lets you dispatch a single. This lets you dispatch a single PDD action. You pick which PDD action you want to dispatch, and these are loaded dynamically from the domain file. So these are the derivative actions of your domain. Then you pick the parameters and you hit dispatch. So let's this quite a way. On this side, you have sort of the whole view. At the bottom here, hidden, this is a list of. Can you screen down just for a minute? The reason I moved it up again is because we did the map with the screen up. And I don't want to confuse the robot. So these are the object instances that are currently in one. We have 3 waypoints. Dock, corner, and podium. Go back to ours, and you can actually see them. That's corner, that's dock, and I'm basically standing on podium. And we have one robot instance, and I just added Kenny, because the robot's name is Kenny. And
Because he died.
he was named by children at the kindergarten at the school.
Aww, super. So yeah, that's not that.
And this isn't the first Kenny that he's going to guess. It's Kenny's small avatar. But we can now add some facts. So we said that Kenny's at the corner, and then he's unlocked. And he's not localized. Oh, we know where the dock is. It's at that fact. So these are facts in PDL1. We can add them in here. This is really just for convenience. Ideally, the model is going to be altered dynamically from sensor data, and you'll see that happen in a minute. But you also want to be able to get in there and change stuff with your hands. And this means you don't have to find the problem file and alter it in a text editor. You can do it straight from the RPG window. So let's also add that the robot is at the dock waypoint is a goal. And I could add that localized is also a goal, but I believe that being localized is a precondition of movement, so I shouldn't have to add that as a goal. When you're done, you can just click plan, So now we localize it. You can see the first thing that this localized action has done is scatter the AMCL particles. I'm going to make it stand here. He's not learned their right. We're going to give our hands because we're on a stage. The map that I think ROSPlan interface movebase, which is also part of the repository we downloaded, on a failure of a movement action, it clears the cost maps automatically and also removes the localized fact from the PDO model. So after it fails movement, you're no longer localized. It's close to corner.
There you go, but you got the heading on.
It's doing go to waypoint.
He's mind getting very well.
Don't you dare. Not again. It's going to get you going on that gap. I can get out there. Just try to get.
Go for it. He's not there.
I walk back over there to stop it. It'll be useful. So this is good. I can show you another option. Cancel.
Very useful.
Move basically is recover the data.
I believe the reason why it fails to localize is because there are not enough landmarks.
100% moved more down, didn't move it back up again. And so now it just looks like a solid rectangle and you can't tell which way it's facing.
If there were more landmarks,
Also, these pillars become landmarks. As soon as it sees the pillars, it knows, okay, I'm facing this way.
Really? Because I was kind of hoping that it would see obstacle, 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 and then space.
So
And that
it's,
would be
I
enough.
mean, it's got the position correct. It
Yeah.
just doesn't know whether it's, this is the chairs or this is the board.
Alright, make it better.
So there's localized action, you can slash it also. You can change the accent.
That's like the most useful function.
I mean, it's there. It's still on that side. It's just it thought it was here. It's definitely one of these two positions. I'm sure it's wrong.
Fine, I can see the pillars now. So it is. So it's going to use them. No.
Oh, it's really not doing that localized like that.
Well, okay, yeah.
Oh, that's. The map is good. And maybe open that last one. The map is good. All right. So now you can see these facts of shared as last we saw. The localized facts is here in the list. And also we have something to look at in the problem because we've been planning doing various things. Well, you have to. A problem's been generated. And this is the final plugin of ROSPlan. It's just a read-only view of the PDL problem. If you like to have a look exactly at it.
Well, that should get generated. What?
So that's what generated. Also, you can localize the killing as we did here. I didn't add that. It's just it's localized. It's without the fact itself. It knows it's in the corner. It doesn't run off at all. If I dispatch a new action, let's say let's say go to the dock.
They're ultimately on
Now, I'm not going to just go enough time. So he moves to this way, but just dock.
Michael,
And you'll see that robot at Kelly Dock has been put there now. Also, visiting dock country. And this is just what's in the main file.
can I ask a technical question? So I see that you have localized dock, undock actions, move actions. Well, is it possible, I'm sure it is, but is it easy for the users to define new actions, different actions?
So these actions are being read from the PDO domain file.
Yeah.
So if you give it a different domain file, these drop-down boxes will have different actions inside them. They're not pre-described, they're just loaded automatically from the knowledge base. So if anyone feels confident altering the domain file now, you can have a go and see what you get the robot to do.
But these actions have to be mapped to the actuators of the robot, right?
That's right.
Like, for example, a move action has to be mapped to the...
Yes, so this is the purpose of those three interface nodes that are running. They're receiving PDL action and converting it into, so we'll basically suggest an example of this again. In the model, we have the robot is at the dock, so the robot at Kelly Dock is true. In the C database, there's an entry with the key dock and the value of the coordinates. When the ROSPlan planning system dispatches the PDL action, goes to dock, it's picked up by the interface component. So these are easy to write. They're less than 50 lines of code because you can extend an action interface template class. And all you need to do is say, okay, when we reach this method, that means we have to do the action. And if you have the PDL parameters about the actions, you say, okay, what we care about is the waypoint that we're going to fetch the coordinates of that from the DB, pass that to MoveBase. And then when MoveBase returns, it will automatically, in a superclass that you don't need to run, it already handles passing feedback to the planning system, fail, succeed, time out, cancel. And also will update the model automatically based on the effects of the action. So it will alter the model, if the action succeeds, that is, it will alter the model with the effects of that action. The model can also be altered as this is the main type of interface component that connects ROSPlan to the platform. The other kind is just listening to sensor data and changing things in the knowledge base. So one thing I can do is write a node, I don't know how big it would be, but not very, that just listens to the positional data for the robot and then updates the knowledge base with whichever waypoint it's closest to. So that this fact, robot app, whatever, is just automatically updated all the time. I don't do that because I haven't needed to so far. But it would be quite useful in some situations. For example, if an action fails halfway, you don't need to worry about changing the form instance to have the robot's new location. It's just sorted out. Yeah. Any questions about ROSPlan or the terminal model as a whole?
Does the dock emanate any sort of signal so that it can dock safely without you having to be super specific about their relative positions?
Yeah, so I forgot to actually record what the dock's position was. I put some tape on the board so I knew how high to rise. I'm going to be coming today. Let's take a look at the college. Okay. I don't know how white it is, but this is the dock, and there's a little red light here. That's infrared as well.
Ah, okay.
And the Kinect can see it. When you ask it to dock, it's going to turn around until it sees that light, try to center itself on that light, and then it will ram into the dock as hard as it can, smash it from there. And
That
then,
sounds like a good idea.
and then maybe it will start charging. It's not so bad, so I can dispatch, let's dispatch a more interesting plan. So let's move that goal. Network is all over again. It's because it's images on. There we go. So let's say that the goal is that he's docked and has visited podium. Which are connected to access gates. And downloading movies.
Do you use my laptop?
No?
Okay. I'll ping you.
Here you see some of the output at the bottom there from ROSPlan. KD is knowledge base. So this is the move-based interface that I described a moment ago, just saying that it's received this response upon it, and then the knowledge base is filling out all these changes to it.
So while we were Wi-Fi is preparing itself, can you talk a little bit more about how you can update the knowledge base based on what you find below?
Yeah. So let's do that from here. So it's on the Wi-Fi, but it's just not heated. How does that work?
You wanted to be more assertive.
Lost topic list. I can't see what I'm doing now. Okay, so this is a list of all of the what does it look like?
Michael,
Yeah?
so which interfaces do you currently have in ROSPlan? You have MoveBase that makes the relationship between PDDL and ROS. You have,
So on the slides I linked the
I missed that part.
I never showed this, it's okay. We'll just search for those parts.
It's only because I'm personally interested in your work.
So this is the main ROSPlan repository. You have the meta package that has nothing in it. Demos has a host of launch files and waypoints files and stuff like that. Everything with messages is just messages. It's very useful to separate messages out from nodes in your packages, so that if someone else wants to communicate with your software, they don't have to be able to compile your software to do it. They just need to compile the messages. Which means you can both continuously work without constantly having integrations. So here's the planning system and the knowledge base and knowledge messages, and then the RQT plugins that I just showed you. So the two interfaces that are standard in ROSPlan, you don't have to use them, but you get them, is move-based and mapping. Mapping is doing the scan matching and localization. Move-based is just doing pathfinding and moving. Then, if you back up, we have a number of repositories here. This is what I downloaded for the Turtlebot, which includes 3 nodes. The automatic docking, so a PDL action for docking, for localizing, and Talker just makes it speak. All that does, it listens to the action dispatch and reads out the name of every action that's dispatched. So I am doing it. Go to waypoint, whatever you want it to say. We also have ROSPlan interface Coda 2. Now, just one class. This is integration with the Coda 2 architecture for autonomous underwater vehicles. They don't use loop base because they don't have a base, and they're also in 3D, and the coordinate system is different for them. They use Y's up and down, I think it's a set. I can't remember which one that is. And Coda 2 is a control architecture for the vehicle. It does all things like pathfinding and localization, battery management. And we have PDDL actions to control how actually you go to the airport. The name's not much different, but the interface of those are different. We're using Coda 2 one is the remove-based one, and then we can run on this something. Finally, I've created a little list at the bottom here. We have, I put it in, you can't see it. There we go. There's one more possibly you can download if you are using drones. This guy, whose name I cannot pronounce because it does not sound like it reads.
Who is this guy?
Yinjik.
It's strange voicing. He implemented these actions for the quadcopter and ran them as a ROSPlan interface.
Is it for the parrot drone?
Yes, it's for power. We don't have power, so I haven't tested it.
Sarah's got a parrot.
Yeah, it's the couplet, isn't it?
Sarah's got a parrot. Yeah, she's upstairs actually.
So we can take it home.
I think it's a King's one. Well, we can try.
One of the battery packs is there, so that's the format.
So I recommend if you go to the ROSPlan GitHub, go directly to the wiki. Because here the installation, the sort of, essentially the tutorial I just gave in the setup is described, as well as there's an architecture overview and some in-depth discussion about how the planning system works and, for example, writing the component. So it tells you, you have to go to package, the header file, source file, to make this in a general way, and then gives you this example PDDL domains. Here's an example go to waypoint action. And then this is the header file, and this is the class file that maps it. The class file looks a lot long, but it's going to put a lot of unnecessary stuff. Essentially, it takes the parameter from the PDDL action, takes the pose from the Mongo database, and that's where it dispatches the Windows action. Everything else you don't need, it returns to the reports. But this also does that, if the action fails, it delocalizes the robot and it clears the cost maps. Only to do some other stuff that makes the action more robust. So, are there any more questions?
Sorry, I have been interrupting a lot. But I assume, there's no component yet that enables you to use the touch sensor of the robot in PDDL.
The touch sensor?
Yeah, there is. The robot has a touch sensor, right?
Yeah, there's a bumper that if you touch it, it retreats.
Does it take it into account in PDDL? Maybe you can.
So no, nothing exists in this. It's not in the PDDL one.
Yes.
But you could add that to the PDDL.
Yes.
Then.
But then you have to create a C++ code to map the bumper feedback to the precondition.
Or you can also use Python for ROS if you're familiar. You should also send messages and call services from the command line, which means that it's a really simple component. You can just write a bash script to subscribe and then put it into the on-the-one. So the bash script would be sufficient for that. I think the output from the bumper is a point cloud, like the one that showed Victor Space on, which is way too much. You could probably find a topic somewhere that's outputting a Boolean value whether or not the bumper is pressed. And then based on that,
yes, in PDDL, you know that there may be an action that whenever the bumper is triggered, it may generate or trigger another action, set of actions.
So, I mean, this is the point of ROSPlan, so now you have a system, you can think about, okay, what's the domain file going to look like? Let's think about the planning model, and you don't actually have to worry about the implementation of actually listening to that sensor and dispatching it. It's fairly simple just to set it all up.
What if you, because I saw that it sort of automatically reduces when you press the button, even though bright light comes and doing anything to change that.
Yeah, so that's one of the nodes button that does that.
Okay. The planner, I mean, it clearly updates the
In one of those total launch files that I included, you used to do that. It's best not to need to know unless you should know in case it's suddenly stopped working.
It was hypothetical.
No, if everybody has a plan for the moment, you probably not want it to do something else.
Not too bad.
What's wrong with this? Right, if this ever wakes up, I'll make it do one plan, and then if anyone wants to come up here and play with the interfaces and get it to do stuff, maybe change the domain, you can do that. If you simply want to stand in front of the robot while someone else is trying to make a computer plan, then you can do that and see what works. If you want to see if you can trick it into jumping off the stage, that's okay too. I wanted to visit the podium. Something tells me it's not there. There you go. This is where you know if I have that plan.
I can do that. Talk.
So the plan in this case was very simple. Did you manage it?
Wherever it is. Oh.
It's time to dock. I'm doing a bad job. You're slow to sell that. Too slow.
Has it just sort of half docked?
I don't really want to say what it's going to do right now.
Because like,
It's a bit grotesque. And that's too much. I mean, that actually is, I actually like that piece of code. That comes with the terminology, right? And it works most of the time. Half of the time it docks smoothly and that's it. Half of the time it does that. That one was relatively smooth. Okay, I'm finished now, but I'm going to hang around here and leave this out for anyone who wants to go there. Thank you for coming. And I hope you enjoy it.
That's presumably put to matters, right?
So it's natural.
Sorry? No, just how does that Okay. So,
There's some figured out sort of three positions of dock effects should be some of the parameters that have to be assessed.
yes. And the robot, and then basically